Okay, so we're going to talk about the unit circle and trigonometries. So I want to start with a quick brief history. Understanding why we do stuff is pretty important. So we can trace back some of the unit circle to the 5th through the 12th century, where Indian mathematicians from India were using 1 as a radius for a lot of the calculations. And then when we move to the 8th through the 14th centuries, it became well known that the Islamic mathematicians formalized the relationship between geometry and trigonometry and connected it to the unit circle concept. And then in the 16th through the 18th century, two famous guys we've talked about, Rene Descartes and Euler, were known for connecting trig to algebra. Now, the idea of trigonometry, we use it for all kinds of science and tech applications, and so on. So one thing I was curious about is, where do the names sine and cosine come from? And we can tell from this little excerpt that we had some pronunciation of names. And so we see the name tangent here and some of these other names. And you can kind of pause this for the history of what those names are. Okay. All right. Now, there are 6 trigonometric ratios. We have sine, we have cosine, we have tangent, we have cosecant, secant, and cotangent. So that idea of will become important later on in your study of trigonometry. But those are your 6 ratios. And so if you look at sine, if you take the reciprocal of sine, you get cosecant. If you take cosine and take the reciprocal of that, you get secant. And then tangent, the reciprocal of that is cotangent. Okay, so what we want to look at here is if we have a triangle with unit 1 radius. Okay, so we have a circle and then we put a triangle inside it with a radius of 1. And let's say the angle is 45 degrees. Okay, so what we can figure out is through Pythagorean theorem, because it's a 45-degree angle and a 90-degree angle with the x-axis, we can use Pythagorean theorem and figure out that the side length is square root of 2 over 2. Okay, now because both sides are the same, both lengths are the same as well. So what we can do then, if we look, the value at which the coordinate, sorry, let me get my correct pen. Okay, this value here has coordinates of the square root of 2 over 2, comma, square root of 2 over 2. So the circle has all these different values, and the largest x value could be as 1. The largest y value could be as 1. And then if we go over to the left, -1 is the furthest left we can go, and -1 in the y direction is the furthest we can go. So these triangles will change shape, keeping the radius of 1, and the coordinates will change as well. Okay, so that's how we can figure out these coordinates using what we know with Pythagorean theorem. Now, what happens if we have a triangle that has a 30-degree angle? So if it has 30-degree angle, what's important is that it came from an equilateral triangle. So this side length, which we're calling y, the y coordinate, is going to be half of the radius. So in this case, the radius is 1. So that y value has to be 1 because that triangle was cut in half. So if we can plug in 1 and 1/2, we can figure out that the x value is going to be the square root of 3 over 2. Okay, square root of 3 over 2. And so now we have our coordinates for that. If we were to do the same process for a 60-degree angle, we would find out that the other values would get switched. So now our x value is 1/2, and the y value is the square root of 3 over 2. So when we look at this, these are 3 common special triangles, and where we can find the coordinates of those points. So that becomes pretty important. Now, we haven't really talked about too much trigonometry. So what we want to do next is look at what happens with these 6 trig ratios. So sine is defined as opposite over hypotenuse. Cosine, adjacent over hypotenuse, and so on. You can read those ratios in the table here. So what happens if we want to take the cosine of 60? Okay, so if we look at the picture in this unit circle here, cosine of 60 is going to be this unit x right here. Okay, and then it's going to be divided by 1. So if we were to substitute this into the calculator, we would get a value of 1/2 for cosine of 60. Now, if we were to do the sine of 60, we would end up getting a value of the square root of 3 over 2. So if we look at the coordinates then, from the prior example above, we see that the cosine is 1/2. And if we look up to the above example, we can see that the value of 1/2 is the x value. So what that means is that cosine goes with x, and that the sine goes with y. So this becomes pretty important in terms of figuring out what the x and the y coordinates are and how they relate to the angle and the trig functions. Now, if you wanted to do tangent, for example, that's going to be your sine divided by your cosine, or your opposite divided by your adjacent. So when we look at this chart and we substitute the numbers in the calculator, we would get tangent of 60 is equal to approximately 1.73. And if you take the square root of 3, you're going to find out that's 1.73. So all these ratios make sense, and they all relate to each other. So this is the first example of seeing how sine, cosine, tangent are related to each other. Now, if you wanted to look at the cosecant, secant, and the cotangent, you would find that these ratios are related in a very similar way. So now, the next thing we want to talk about is if you know two sides of a unit circle triangle, then you should be able to find the ratios of the other trig functions of all 6. So for example, if we know that the cosine of 60 equals 1/2, can we figure out the other ratios? So keep in mind that 1/2 is really 1/2 over 1. So our adjacent and our opposite are defined in this box. So we can now substitute these values in. And, the hypotenuse is 1 because that's the radius of the unit circle. So we have all 3 of these. And you can see how all these values can be calculated just off of the 1. So we have our sine, our secant, our cosecant, which has to be simplified, our cotangent, and the tangent as well. So all of these values are defined. So that's one thing that you'll have to do is given an angle, with the radius of 1 and one side, can you find the remaining trig function ratios? All right, so next, if we look at the first angle on the right, if we have a 60-degree angle, we have the coordinates, and we've been working with those coordinates in the last few examples here. Now, what happens is this degree from the x-axis, okay, so 60 degrees from the x-axis here, is what we call a reference angle. So any measurement from the x-axis is what we call the reference angle. So if I were to graph 120 degrees over on the left, then the distance in terms of degrees, the amount of degrees to the x-axis, is going to be 60 degrees as well. And these are, again, what we call reference angles. And these are going to become really helpful for us as we try to navigate around this unit circle. So if we want to look at this, I kind of drew the diagram here of the angles that all have a reference angle of 60 degrees. So you can see the 60 and the 120 we talked about. Now, if we know that this here, we're starting at 180 degrees, and if we add 60 to it, it takes us to 240. And we know that over here would be 360, and if we go backwards, that's going to take us to 300. So we can see that all of these have reference angles of 60 degrees. Okay, and then here's the chart down here. If you are starting from 0, we're going to add 60 or whatever the angle is. If we're going from 180, you're going to subtract to get in quadrant 2, and so on. So that would be the formula of how you do it. Now, what does this tell you? Well, this allows us to easily determine values for a certain trig function around the unit circle. So for example, the cosine of 60 is 1/2, which we've calculated above. Now, if I wanted, and we also know the cosine is the x value. So if I took that 1/2 and I went this way, it still would be 1/2, but now it's going to be negative because it reflected over the y-axis. Your x values, where 120 degrees are now negative. If I go from 120 all the way down to 240, the x value stays the same. So that's why we have 240 is equal to negative 1/2. Now, if I go all the way back over to 300, we see that now we're in the positive x value range. And so we have a positive 1/2 for our cosine of 300. Okay, so this pattern would be very similar with sine, except with sine, we're talking about the y values. So if we did sine of 60, that's going to be positive. If I go sine of 120, that's also positive because those are the y values in quadrants 1 and 2. When you do sine of 240 or sine of 300, then our y values are going to be negative. So what this does essentially is our reference angles allow us to locate, what the signs are and what the values are for each of the ratios in each of the quadrants. So you can see that in quadrant 1 out here, all the values are positive. When you go to quadrant 2, okay, the sine is positive, that's your y value. The cosine is negative, and your tangent is sine divided by cosine. So positive divided by negative is a negative. And then we end up in quadrant 3. And we see that we have 2 negatives, which means the tangent is going to be positive. And then in quadrant 4, okay, we see that we have a negative, positive, and a negative. Okay, so that's kind of how we navigate around the unit circle, starting from where we were. Now, where does this take us? So next is what happens if we want to calculate the length of the circle's arc. Okay, so we know we can calculate the coordinates of the point, but what happens if we want to know on this circle, how far is it to that point if I follow this curve? So what we can use is our idea of circumference of a circle. So if we know the radius or the diameter, we can figure out the entire circumference of the circle. So in a unit circle, the radius is 1. So our circumference is going to be 2 pi. So one circle distance around is going to be 2 pi. A half distance is going to be pi. And then you have your quarter distances here as pi over 2 and 3 pi over 2. So what we can do to figure this out is we have a new arc length formula, slightly different than a geometric formula. Our theta is going to be the radians. Okay, now we know it's radians because a measurement almost always is going to have a pi associated with it. And then we multiply it by the radius, which in this case is 1. So for example, what is the arc length in radians for a radius of 1 if the angle is pi radians? So pi radians times 1 gives you pi. And so if we were to figure out the arc length going all the way around to pi, it should be pi radians. Okay. If we went all the way around the full circle, it would end up being 2 pi radians. So this shows us how the formula works. Now, one thing that might have to occur is to convert these values from degrees to radians or radians to degrees. So we have this table here, this little ratio table, where if we take pi, that's going to be with the radians. And if we take 180, that's going to be in degrees. If we cross multiply these values, like so, we get what's in the box here. Now, this little box would be really handy to memorize because it allows us to now convert whatever we need to based on the information we have. So, for example, if I wanted to convert 360 degrees, that's a really common conversion. Okay, since it's in degrees, I'm going to replace the degrees here on the left, and I get 360 pi divided by 180. Now, I'm going to divide both sides by 180 because I want to solve for the radians on the right side. And what happens is we get 2 pi radians. So we go back to the distance around the unit circle, and the unit circle circumference, because it's a radius of 1, is 2 pi. So 360 degrees is equal to 2 pi radians. So that holds true. Now, what happens about those triangles we talked about earlier, like a 30-degree angle? Well, if we substitute in 30 for our degree, and then we divide by 180, we'll end up getting pi over 6 radians. So that is going to equal to 30 degrees. Okay. All right, and we can do this for our other values of 90, 60, and 45, and we can find all these values, convert from degree into radians, and it creates a nice little reference for us where if we have 45 degrees, okay, that's going to be pi over 4. If I have 30 degrees, that's going to be pi over 3. And then I have down here 30 degrees, pi over 6. Okay, so we have all these values, which is quite nice. Oops, sorry, made a mistake. Pi over 3 is not here. Okay, so we have pi over 6 here, and then pi over 3 would be somewhere up here. Okay, so then we have our 30, 60, and 45 degrees angles with the conversions. Okay, now this is going to help us now find trig values of common radians. So, for example, if we wanted to convert a common radian, such as 30 degrees, we end up getting pi over 6. Now, what is pi over 6? That's the 30 degrees. So if I wanted the cosine of pi over 6, or the sine of pi over 6, it's the same as taking the sine or cosine of 30 degrees. Okay, and this process will be the same for 45, 60 degrees, and 90-degree angles and their reference angles and sines. So with some practice, we can use the reference angles to determine the signs of these the values, such as half or negative half, and convert them as needed with the common radians. Now, one last topic we need to talk about is this idea of coterminal. Coterminal is if you're given an angle, it's the coterminal angle is another value that it equals by adding or subtracting one full circle's circumference, which is 360 degrees or 2 pi. So in degrees, you can see here, we can take the degrees plus 360 and the degrees minus 360. So I created a 50-degree angle in this circle. And if I add 360 degrees, the coterminal angle, one of them, would be 410. If I take 50 and I subtract 360 degrees, that's going to give me a coterminal angle of 310. Now in radians, say I had 3/4 pi. Well, I'm going to add 2 pi. That's one full circumference, which takes us to 11 pi over 4, which is 2 3/4 pi. If I subtract one full circumference, that's going to be a minus 2 pi. And when we do that, we get a value that is not correct on the screen. Okay, it's -2, and then we're adding 3/4. So that is going to be -1 3/4. Okay, so there we have our values using coterminal angles. With all this information now, what kinds of things are you going to be asked to do? Well, if you're given one trig ratio, you're going to have to find the other 5, which we talked about briefly. Can you evaluate a trig value if it's in degrees or if it's in radian form? And we have common degrees and we have not so common degrees. Can we identify the reference angles both in degrees and in radians? Can we identify the quadrant a value could be found? For example, cosecant of 235. What quadrant, and would it be positive or negative? Can we also calculate the arc length of a given degree or radian measure? To do some of this stuff, we're going to need to convert from radian to degree or degree to radian. And then in general, we should really know these values of the common angles, 0, 30, 45, 60, and 90. And then we're able to move these around the unit circle based on the things we talked about above. And finally, can we find coterminal angles if we're given an angle? So there's lots of different things we can do based on this information. A lot of information was shared, and so it might be helpful to go back, watch it part by part, pause it, take additional notes if needed, and use this to help you study for the upcoming unit on unit circle and trigonometry.